going to start out with 7.1 here, the idea of a sampling distribution. Starting out with this unit, we're going to talk about parameters and statistics. And we're going to talk about what the difference between those are, not only in definition, but in symbols as well. So with this, we're going to talk about the statistic first. So for our statistic, that is going to be the number that describes a sample. So again, the statistic is the number that describes a sample. Describes a sample. Okay, and the other thing we're going to talk about again is parameter. So parameter, we're talking about the number that describes a population. So parameter is the number that describes a population, or the population, but we'll say describes a population. Describes a population. So again, remember that statistic is the number that describes a sample, as to where the parameter describes a population. It's the number that describes a population. Okay, so now let's talk about the different symbols we're going to use for dealing with this on a little two-way table. Let's make it. So let's make a little two-way table. We'll start out with parameter up top, and we'll deal with our statistic underneath that. Since our parameter is mainly talking about the entire population, as to where our statistic is talking about our sample. Okay? And with this, we'll talk about three different terms that we need to worry about for these two. We'll talk about the means. And we'll talk about the proportion. And then we'll talk about the standard deviation. So the symbols for these is quite easy. We've kind of seen them off and on a little bit. So for the parameter for the means, the overall means for a population is given by our mu. The proportion is to be signaled by a capital P, and the standard deviation is going to be lowercase sigma. That is for the parameter. Talk about the parameter of your data. Okay. Now, the number that describes a sample, statistic-wise, your x bar is going to be your means. For the proportion, you're going to have a p hat. So a p hat. And for your standard deviation, you can simply label that as an s. Okay, so again, parameter is talking about the number that describes a population, statistic, number describes a sample. Therefore, these are the types of symbols you'll use to differentiate between the two when you're dealing with a problem, okay? So let's look at a little bit of a problem here and talk about this. So let's say that I had a small class. Let's say I had only 4 people, right? Only 4 people that took the last test that we took. And with that, let's say they got the scores of, let's say what test it is. Let's call that Unit 4 test. We'll say on the Unit 4 test, the grades were a 60, a 70, an 80, and a 90. Okay? So with that, let's make a little dot plot and see what we would have for this. Again, to make a dot plot, go ahead and label it. So to make a dot plot, let's say we have our setup here. We have a bar, and then we'll just do it in tens as we're going at tens. We'll say we got 60, 70, 80, and 90, right? And again, if you had to put those in dot plots, you have a dot on 60, dot on 70, dot on 80, and a dot on 90. So with that, what does each one of those dots represent? The score, right? The score for each one of them. Okay? So a nice little dot line here. So now, let's say we took a sample of any two of these scores, and we need to find a mean. So again, this is our population, right? These four are our population. Okay? So let's say we just take two scores. So we were to take two scores and then find a mean. So let's say we took 60 and 70. Okay? Well, if we were to do that, of course, pretty sure you guys understand how to make a mean here. We take 60 plus 70 and of course divide by 2. And that would give us 65. Well, now for the proper notation of this, we are dealing with, again, this is a statistic, right? Statistic. So this is the number that describes a sample. We took a sample. We took 2. This is our sample. So therefore, we would say our X bar is 65. Okay? So now let's say we needed to figure out all the possible samples of size 2 and calculate a sample mean of each. So in this case, well, we've already got 60 and 70. Well, then we'd have to do 60 and 80. We'd have to do 60 and 90. We'd also have to do, let's see, we'd do 70 and 80. We'd have to do 70 and 90. Okay, and then we would need to do 80 and 90. Make sure that 9 looks like this, so it doesn't look like 70 and 70, so 90. Okay? So therefore, that should take care of all of the combinations there, because anything else, let's see. Yeah, it'll take care of all of our possible setups here without having any repeat values, okay? So we should have 6 figures altogether. So in this case, then we did 60 and 80. That would give us our sample mean of 70. 60 and 90 would give us our sample mean of 75. 70 and 80 would give us our sample mean of 75. 70 and 90 would give us a sample mean of 80. And then our sample mean of 80 and 90 would be 85. Okay? So if that's the case on that, then let's go ahead and make a dot plot for all these figures we just found. Again, let's just draw this out real quick. Shouldn't take too much space. So we'll draw a little line here and we'll say, let's start at our lowest value was 65. So we'll start out at 65. We'll go by 5. So it seems to go in 5s here. Okay. I think I made the stops at 85 there, looks like, but I went up to 90 on my little scale there. And let's see what we got here. So we would have a dot at 65, a dot at 70, a dot at 75, another dot at 75, a dot at 80, and a dot at 85. Okay, so with this, let's see what we got. We've got a pretty symmetric look on this, right? Kind of a bell shaped, as we can look from that and see it's kind of a bell shaped look. And so what does each one of those dots represent? That's what I want to know right now. What does each one of these dots represent? Well, like let's say right here on number 85. Let's say that one That dot right there is going to be one sample of 2 with a mean of 85. Alright, so again, I'll write this out for you guys. This is one sample one sample of 2, because we took 2 scores, with a mean of 85. So we took 2 scores, and we got a mean of 85, so that gave us 1 dot. So that's telling you what each dot represents. Now, what would be the mean of our population? Well, we have our population up here, right? So what would be the actual mean of that population? Well, just as you took for our sample, you would take all 4 of these though, add them up, and divide by 4. So we took those 4 values and divided by 4, you should get a value of 75. And the proper notation for that, for this value, of course, because we're dealing with a population, right? Our actual notation would be a mu. A mu is equal to 75. Okay? So again, for our sample means we're dealing with x bar, alright? For our population mean, we're dealing with a mu. And then understanding, they may ask you on time from time there with, as far as on a dot plot, what those dots represent. So understand what those dots are representing there, which one sample of 2 with a mean of 85. Okay? Alright, so let's go into this and talk about the biased and unbiased estimators at 7.1 as well. So unbiased estimators is a statistic, is an unbiased estimator if the mean of the sampling distribution is equal to the parameter. And then we're going to go into talking about variability. And talking about increasing the sample size will decrease the variability of the statistic. Then we'll go over a little example here on how that plays out. So let's say I got some data values for the Judson High School statistics class on their last test. Let's say it was their Unit 4 test. And Mr. Walker, the stats teacher over there at Judson High School, gave me those data values. Well, and then I gave those values to you guys, each one of you. So since there's 19 of you in class, I then told y'all, out of all the data values they gave, to take 5 of the test scores and get a sample mean for that. And then I told you to do that 5 times. So each one of you does that 5 times. Y'all take 5 scores and give me a sample mean. So that'll come out to be on 95 different data values, right, for the sampling distribution. So 95 different sample means for this. And that would give us this dot plot right here that I played out for you guys. Now granted, I came up with these numbers, but that's how it would play out, right? We'd come up with this dot plot for the sample. So again, the sampling distribution, this is sample mean, so is our sample mean, our x bar, okay? So with that, let's see, where would our mean fall? Well, the mean will fall right here on 77, right? So our mean of these data values should fall on, for the sample distribution of x bar, should fall at 77, okay? So what does each dot on this poster represent? Okay, let's think about it again. What does each dot on this poster represent? Again, each dot, so we take one of these dots, this is simply saying this is one mean from a random sample of 5. So one mean from a random sample of 5. A random sample of 5. Okay. Okay, so we know that, and then it gave us the overall true mean for this average, right? So the overall true mean, as we listed up there, as a horrible mu. Let me draw that again. the mu of 77. So the true mean of this data values for these sample distributions came out to be 77. Alright, so now let's talk about a sampling distribution, alright? So sampling distribution shows the statistic found in all possible samples of size n. Well, we did of size 5, right? Our sample size that we did, our sample size n was 5. So with these data values we got here, again I said I got 95 of those. Was that all of the possible arrangements of 5 scores to get the means of those? No, it was not. Because if we were to do that, we could do the combinations, right? So we'd take combinations of, we had 95 total, and we took a sample of 5 each time for the 95, right? And that would give us our value. So what would we get here? So if we did that in the calculator, so say we pulled up and we took menu, and we did probability, and we did combinations, because we want to eliminate the repeats. So therefore we use combinations, and we did again 95 was the amount we had, and we were taking a sample of 5 from each one. And therefore we would have, looks like 57,940,519. Okay? There's it over here so I can see it and still write it out. So we should have 57,940,519. So 57,940,519 combinations, and we only came up with 95. Okay, so therefore we did not have everything for a sampling distribution, right? We didn't take all the possible samples. So again, this is all the possible samples of 5. All possible samples of 5, okay? And we only did 95 possible samples of 5, okay? So again, let's say we look at this data as well. And since we did all this, let's say, since this was at Judson High School, let's say we took a random sample of 5 of these test scores here at Veterans Memorial High School. And let's say we got a mean of, let's say our mean now, our sample mean that we got at Veterans Memorial, let's say that mean was 68. So you guys struggle a little bit on it, so you only got a 68. Well, is there convincing evidence, shall we say, is there convincing evidence that you guys did worse than the students at Judson High School? Well, to do that, let's look at this. Again, we had 95 samples altogether. We're looking at from 68 and going this way, right? So we would have 1, so 4 is 5, so we'd have 8. So we would have 8 over 95. And with that, that should give us 0.08. So 8%. Okay? So if we have 8%, so I would say no, because there's only an 8% chance, or not only, but there is an 8% chance of getting a sample mean of 68 or less purely by chance. So again, when we look at these and we're trying to find out if it's going to be convincing evidence, we want to use 5%. So convincing evidence, you need to compare, I'll put O, compare to 5%. In this case, if it was less than 5%, then yes, we would have convincing evidence. If it was less than 5%, we would have convincing evidence. But since we're looking at 8%, I'm going to say there is not convincing evidence since we have 8% chance. Since there's 8% chance of getting 68 or less, purely by chance. Purely by chance is a key statement to put in there, okay? And we're going to say purely by chance, and then also list what the overall parameter is for the population. So our mean value, right? Purely by chance, if that mean is 77. So no, we wouldn't have convincing evidence since 8% of the chance we wouldn't have convincing evidence since there is an 8% chance of getting 68 or less purely by chance, okay? If that mean of the population is 77. So our parameter value is 77. All right? So again, think about that when moving forward with these and comparing convincing evidence. Compare it to 5%. If it's less than that 5%, then yes, you would have convincing evidence. If it's greater than, you do not have convincing evidence. Okay, so now let's look at our variabilities, right? And when we talked about up here, when we talked about increasing our sample size decreases variability of the statistic. So if we were to do that, let's say we went through the same setup, right? So over here on this one, right? We said that our mean overall for this population was 77, right? And that's where it fell right here. Okay? And we had done, there was 95, so our sample size on this one, or n, was 95. Well, instead of us each doing, all 19 of you doing 5 samples each time, let's say the 19 of you just did 1. Right, so each one of y'all just took 5 test scores and got a sample mean once. So therefore, our sample size on this side was 19. So it was lower, right? Instead of 95, only 19. And then with that, our mean value here, the mean value, if we'd only done 19, the mean value we got for the population would have been around 81. So with that, that's when it falls into being biased, right? Because this was only a 19, a smaller sample size compared to our 95. And we got a better value for the mean. So in this case, since the mean value was higher, our mean value for only 19 was sitting over here at 81. Okay, so therefore that's when this is a biased setup. This is a biased for the whole population. However, if we were to do this and stay with our 95 for the whole population setup for it, then it's not so biased, right? This is more of an unbiased setup. This is unbiased because it's closer to the actual value, if not right on the actual value of that. In which case, let's look at that real quick. The actual mean value I got from the test scores from Judson High School, from Mr. Walker, for that test, the actual mean overall for it was 77. So therefore, because it actually came into when we did this with our 95 samples, came out to be an average, or the mean value came out to be 77, it was unbiased because of the statistic mean estimator, right? So with this value, it came out to be 77, squared is the same as this. And with that, with notation wise, you probably caught on here, it looks like I used the wrong notation here. I was getting to think of the mean overall, right? So again, this isn't the mu, because these are just dealing with our sample mean. So the mean for all these samples was 77. Just like over here for these samples we did, it was 81. So hopefully you caught on that. I apologize for making the mistake. Got a little tied up with my notation. So again, these are for the sample means of this, and the sample mean overall was 81 for only 19, and then it was 77 for when we did 95. But the overall parameter, the actual population, the values they got for Mr. Walker was 77, and because that equal to the mean value of our sampling distribution of 77, therefore it is unbiased. However, if we just did this where 19 values were created for this, that would have been a biased setup because it would have said they got a lot higher average than they actually did because they only got 77 as to where we would have calculated 81. Okay? So that is understanding the difference for the biased and unbiased estimators. Hopefully it makes a little bit better sense. Alright, so hopefully that helps you out with dealing with the check your understandings, and I'll see you next time.